There we are. Good morning, lads and ladies. Welcome back to MAP2302 Differential Equations. As promised, today we are going to discover variation of parameters. So I'm going to go through the derivation of that formula. I'm going to explain all the terms to you, and we're going to see how it generalizes to higher dimensions. So the formulas I gave you last time were for second order equations. The same thing can be done for higher order equations. I'm going to go through the proof in the case of the second order equation, because you don't really lose any generality. It's just there's like a lot more symbols to write down if we look at third, fourth, fifth order equations. So I'm going to prove the formulas that I kind of gave you last time. I'm going to review something called Cramer's rule, which is a really nice way to understand where the solution to that linear system at the end comes from. And then we'll see how to use it to cook up some particular solutions to inhomogeneous equations where the right-hand side is not the sort of thing that we could normally solve using, using the method of undetermined coefficients or annihilator operators, however you want to think about it. So here we go. Disconnected. Okay. So this is MAP2302. It's a lecture, and today is 7/22, the 22nd of July. It really is crazy how fast these 6-week courses go. I've never done DiffEQ in a 6-week semester, and shocking, just shocking. I feel like I just met you guys, and here we are already at variation of parameters, which is one of the kind of usually one of the pinnacles of the course. You know, we build up to this, so it's wild. Today we're going to do the following. I want to review linear systems and Cramer's rule. Then we're going to prove the variation of parameters formula. In the order 2 case, and we'll discuss variation of parameters for higher order equations. And so that's sort of our roadmap. I'm tempted to say we can talk about Cauchy-Euler equations because it feels like we might have time, but I promised you guys yesterday that I wouldn't cram that in there, so I won't. I'm gonna force myself to hit the brakes a little bit on that. Give me just 1 second. All right. Sorry, the kettle's going off in the background. If you hear that, it'll stop in a second. Linear systems, right? Linear systems. This is something you learn about in pre-calculus, and then sometimes you play with it a little bit through the calc sequence, specifically in Calc 3 when you learn how to change coordinates and higher dimensional integrals. You usually have to work with some determinants there, Jacobians, if you remember the Jacobian matrix and the Jacobian determinant. But Cramer's rule is something that often people just forget about. It's not really a big deal because you can solve the relevant linear systems usually, through other methods reasonably fast. But Cramer's rule turns out just the way that Cramer's rule has you write down the solution to a linear system is the nicest way to express the result here for variation of parameters, because it's given in terms of determinants, and the Wronskian is going to crop up there. So let's start with this. Recall that n by n linear system of equations is a collection of n equations with n unknowns written. So this is going to look a little bit intimidating because I'm doing the full n by n thing. I'll look at a 2 by 2 case. Usually we'd write this as something like a11 x1 plus a12 x2 plus a13 x3 plus, and there you go all the way out to a1n xn, and that's going to be equal to something like, let's say, b1. So that's your first equation. The a's here, a11, a12, a13, a1n, all of those are just numbers, and your variables are x1, x2, x3 up to xn. Then you'd have like a21, x1 plus a22, x2 plus a23, x3, and so on up to a2n, xn equals b2. So here's one equation, it's got n variables, and here's the second equation, and it also has those same n variables. The numbers a11 or a21, a12, a22, they can be whatever you want. And things continue like this. We're supposed to have n equations there, so the last row would be like an1 x1 plus an2 x2 plus an3 x3 all the way out to ann xn, and this would be equal to bn. So, I can write lots of dot dot dots in here. This is sort of the standard way. And usually when we write a linear system, you've seen me doing this, you put the curly brace on the left-hand side. And the goal is to find the values of, I'll call it x, it's a vector, x1, x2, x3, all the way out to xn. You want to find the values of the variable x1, x2, x3, all the way out to xn that make each of these true at the same time. Satisfies all the equations simultaneously. There's so much to say here, right? I can't like teach you all of linear algebra as a brief review to talk about Cramer's rule. But if we write the matrix A as a11, a12, all the way out to a1n, a21, a22, all the way out to a2n, and down to an1, an2, all the way out to ann, this, and the matrix or vector, matrices and vectors, BT-dub, same fucking thing. Vector is a matrix with either one row or one column. Vector x as x1, x2, down to xn as a column vector, and the vector b as b1, b2, all the way down to bn. Then this system, we'll call it star, then star is equivalent to the matrix equation matrix A times vector x equals vector b. Adjust the camera here. Center probably should be all this. All right. So this whole big scary thing can be written in this form, where A is this n by n matrix, whose entries are the coefficients from the system. X is this column vector, whose entries are the n variables that you're trying to solve for. And B is the column vector of right-hand sides. I'll let you check. Hopefully you remember how matrix multiplication works. If you've forgotten that, for the love of God, remind yourself, because there's nothing more important anywhere in mathematics, nothing more important than linear algebra. Check that when you actually write this matrix equation out, like this matrix times this vector equals this vector, you really do get this. The left-hand side, when you multiply, is going to give you all of this stuff. So you have a vector whose first entry is this left-hand side, whose second entry is this left-hand side, and whose last entry is this left-hand side. And that vector of linear combinations of the x's is going to be equal to the b vector. And the only way for two vectors to be equal is if all of their entries are equal. So rewriting a linear system as a matrix equation is sort of your first step to abstracting from like solving with elimination substitution to starting to understand linear algebra in a grown-up way. It's in this setting that it's easiest to discuss Cramer's rule. I'll go ahead and show it to you in a few ways. So this is just preliminary stuff, right? Basically vocab. I know most people are used to seeing matrices probably with the square brackets. I like the rounded parentheses. Okay, so in particular, a 2x2 system, and I'm gonna a 2x2 system, something like A11 x1 plus A12 x2 equals B1, and A21 x1 plus A22 x2 equals B2 can be written as AX equals B. X and B's are vectors. You can put the arrows if that helps you remember. Can be written this way, where A is the matrix A11, A12, A21, A22. X is the vector x1, x2, and B is the vector b1, b2. Bunch of ways to think about it. Linear systems like these. One of the things you probably do remember is that these can have one solution, no solution, or infinitely many solutions. And you can think of it like, how do lines touch, right? We're looking to see where this line crosses with this line. If the lines are different slope, then they'll guarantee to touch at one point. If the lines are the same slope, then either they'll never touch, which would mean no solution, or they're right on top of each other, which would mean infinitely many solutions. Those cases correspond to values of the determinant of A. So if the determinant of A is non-zero, then there's a unique solution. If the determinant of A is 0, then either you have no solution or infinitely many solutions, depending on the right-hand side. And there's lots of great ways to think about this in terms of linear independence and spanning of vector spaces, but that's something for you to learn about when you take a linear algebra class. Here. This is Cramer's rule. I gotta say here, the system has a solution. It's a unique solution if and only if, the abbreviation for this is IFF, the determinant of A is non-zero. If the determinant of A is non-zero, then you can get any right-hand side, guaranteed, by taking appropriate linear combinations of x1 and x2. But Cramer's rule says that if the determinant of A is non-zero, then the system, I'll write it in the 2x2 case, A11 x1, same thing above, A21 x2 equals B1, A21x1 plus A22x2 equals B2 as solution. Here's the idea. What you're going to do is take the matrix A, calculate its determinant, that's non-zero. We're going to be dividing by the determinant, and then the upstairs of each of the component solutions, like x1 and x2, those are your components of the solution vector. You're going to replace a column of the matrix A by the right-hand side. So x1 would be the matrix A with the first column replaced by the right-hand side, and then take its determinants. This would be B1, B2, and then A21, A22, divided by the determinant of A. X2, you take the matrix A, and you replace the second column by the right-hand side. So the first column stays the same, A12, A11, A21, and then B1, B2, and then divide by the determinant of A. If you solve the system using elimination or substitution or whatever, you can prove that this formula works, right? It's not an exciting proof. You just grind out the solution here in full generality, and then you compare to these things, and you realize that they're the same. So if you find the solution to this by row reduction, elimination, whatever, and then you compare what you get for x1 and x2 doing that to what you get here, if you write out all the determinants, and what you get here, if you write out all the determinants, you realize they're the same thing. So Cramer's rule, just a kind of a nice way of writing the system, the solution to a linear system under the assumption that it has one, that is under the assumption that the determinant is non-zero. What we're going to do is take a general second order inhomogeneous linear constant coefficient differential equation, make that assumption that the particular solution is a combination like u1 y1 plus u2 y2, where the u's are not necessarily constant functions, build the ODE, then make an additional kind of weird assumption, and that will lead us to a 2x2 system like this, algebraic equations. That'll give us solutions like x1, x2, but instead of x1 and x2, it's going to be u1 prime and u2 prime. And then we'll integrate those to get u1 and u2, and then we'll go back and plug that into the original assumption that yp is u1, y1 plus u2, y2. And that's your variation parameters formula. It's quite an intimidating formula, so I recommend dealing with it at the level of abstraction you're most comfy. If you're most comfy just memorizing the formula, that's fine. I'll show you the kind of step where I kind of keep it in my brain as like, okay, if I need to use this, here's where I begin working. But let's do that. The reason this Cramer's rule thing is so useful because that's actually the step where I do that. Questions on what Cramer's rule says, linear systems? Has anybody seen Cramer's rule before? Just curious, give me a thumbs up react if you've seen Cramer's rule in pre-calc or somewhere else. Nobody, huh? Oh, interesting. Okay. Officially, by the way, and I know it doesn't always happen in my class. Officially, Cramer's rule is a part of pre-calculus here at Santa Fe. All right. So I'm gonna tuck this in my pocket. And I'm gonna hook up variation parameters. So I'm going to assume a few things, that y1 and y2 are solutions to the associated homogeneous equation of So I'll write this as y prime prime plus p of x times y prime plus q of x times y equals g of x, which is my general second order linear equation, just having divided through by a2. And then in addition to that, we're going to assume that that the particular solution is of the form we discussed, u1, y1 plus u2, y2. What you notice here is I'm not necessarily assuming that p and q are constants. So even though we only know really how to solve constant coefficient equations in the general case, in the second or higher order case, this variation of parameters business will work in other settings also. It can work in the non-constant coefficient case. But finding these so-called null solutions, finding y1 and y2 is hard if p and q are not constant. Okay, further assume that yp is of the form u1 of x times y1 plus u2 of x times y2 for some functions u. This is not an unreasonable assumption. It's following the same sort of thinking that we were using when we proved the reduction of order formula, namely that we're looking for linearly independent solutions. So, you know, like if you just look at this is the assumption sort of that we started with for reduction of order. We said that instead of yp, y2 should be some non-constant multiple of y1. Same sort of logic here. It is the case then that yp prime is going to be, you know, you take derivatives of this and you get, I'm not going to write the x's, you get u1 times y1 prime plus y1 times u1 prime plus, that's the product rule applied to this, just not writing the x's, u2 y2 prime plus y2 times u2 prime. Right, just taking the product rule for this to get this, product rule for this to get this, and our second derivative, yp double prime, is going to be u1 y1 double prime plus u1 prime y1 prime. That's the product rule applied to this. Yeah, a bunch of terms here. Plus y1 prime u1 prime. I'll do y1 prime u1 prime plus y1 u1 prime prime. That's the product rule applied to this. Plus u2 prime y1 prime plus u2 y2 prime prime. Product rule applied to this. Plus y2 prime u2 prime plus y2 u2 prime prime. Lots and lots of terms there, right? 8 terms altogether in the second derivative. We're going to plug both of these into here. And I'm not going to show every single step because it would take fucking forever. So what I'm going to do is I'm going to plug these guys in here and I'm going to regroup and factor some terms. So I've got some prepared notes. Plugging these into, I'm putting my equation numbers over here, into equation 1. Yields the following. After I regroup all my terms, I'll have a bunch of stuff that has a u1, and I'm going to factor the u1 out, and I'll get y1 double prime plus p of x times y1 prime plus q of x times y1. So if I take all the terms that have this U1 factor, if I kind of look for the original ODE with Y1 in there, I can find it and factor U1 out. In addition to that, we'll have U2 times Y2 double prime plus P of X times Y2 prime plus Q of X times Y2. And then lastly, kind of outside of these things, you group terms together until you find those bits of the original ODE in there. And you'll have a Y1, U1 double prime term left. And you'll have a U1 prime, Y1 prime left. Let's see, I'm out of space here. Plus dot 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 plus Y2 U2 double prime plus U2 prime Y2 prime plus, I know, P of X times Y1 U1 prime plus Y2 U2 prime, close bracket. And then the last term, the very last term here is Y1 prime U1 prime and Y2 prime U2 prime. All right, I know that's a lot. So this is what the left-hand side, so this is the LHS. Left-hand side of one becomes that. Right-hand side is just G of X, I'm not gonna write it. Some neat things to observe. Because Y1 and Y2 are solutions of the associated homogeneous equation, these two bits here are 0. Right? That's what it means to say Y1 is a solution of the homogeneous equation. When you plug Y1 in here, you get 0. Y2 is a solution of the homogeneous equation, plug Y2 in here, you get 0. So these two terms are going to drop out. And then some of what's left can be understood as derivatives of other things. Let me go ahead and just, yeah, I'll show you. We'll do all the. Okay. So I see a Y1 prime U1 prime plus Y1 U1 double prime. Y1 U1 double prime, Y1 prime U1 prime. These two terms are the derivative ddx of Y1 U1 prime. Right? If you apply the product rule to this product, you get these two terms. Looking at the other pieces over here, I can see those as a product rule derivative also. That's ddx of Y2 U2 prime. Right? Y2 prime times U2 prime plus Y2 times U2 double prime. These guys, use some color here in a way that will help. This stuff is this. This stuff is this. Just a sort of creative way of recognizing product rule derivatives. And then what else lingers? We still have our P of X times Y1 U1 prime plus Y2 U2 prime, and then the two terms at the end. So this is still here, and these are still there. Okay. So this line right here has everything. The first two big terms were 0. The teal underlined term is this teal underlined term here. The purple underlined term is this purple underlined term here. And then these guys I just bring down. And if we are a little bit more clever at spotting derivative rules, I can group a couple more things together, right? Like grouping this and this and this with this. I can see this is d dx of y1 u1 prime plus y2 u2 prime. That's just putting these first two things. So I'm using linearity of the derivative to group these two together, right? Derivative of something plus derivative of something else is the derivative of the sum of two things. And then we still have our p of x times y1 u1 prime plus y2 u2 prime. And then the last two terms. Yeah, no change to this. Y1 u1 prime, yep, plus y2 prime u2. Okay, and all of this is supposed to be equal to my right-hand side. G of x. So maybe what I'll do, instead of putting equals here, I'll put a period here and say, so we get this. This equation at the bottom is more than a little bit tricky. You've got a derivative of something, and this is y1 u1 prime plus y2 u2 prime, plus p of x times the that same thing, right? y1 u1 prime plus y2 u2 prime, plus something else over here. These terms are equal to your right-hand side. This is kind of looking like your original ODE. And you can think of this as a piece and that same piece showing up here. These are parts of derivatives of those. But at this stage, we're going to make an additional assumption. And this is where people get lost in variation of parameters. If you wanted to cook this up for yourself, this is the step where you go like, what the fuck? Why would anybody do that? For reasons that are, sometimes in mathematics, you come against a problem that is intractable. You say, I'm going to try to come up with a formula for something. I'm going to try to prove something. And you realize halfway through that you don't have all the assumptions you need. So mathematicians will often kind of go back and insert a hypothesis at the very start of their argument. Say like, you know, the most common one is proof by contradiction. You're working to prove something and you're like kind of just stuck. You're like, I just don't have enough to work with on this. So instead of trying to prove the thing you're after, you assume the thing you're after is false and then try to reach a contradiction. And that gives you an extra hypothesis to use, right? The assumption that the theorem you're trying to prove is false is an extra hypothesis. Kind of in that spirit, this piece showing up twice here, it would be nice if those were gone. It would be lovely if this and this were both 0, because then I would just have this left over. Here you have more degrees of freedom than are necessary and more degrees of freedom than narrow down a unique solution. So just for fun, what if we try assuming that these pieces are 0, that y1 u1 prime plus y2 u2 prime are equal to 0. If it turns out that this is too much of a leap, then you can go back and get rid of the assumption, right? That, how would you know if this was too much of a leap? If the resulting expressions are lead to contradictions. right? So if you get something that says, you know, e to the x equals 0 or 1 equals 2 as a consequence of this assumption, then you know that it's not an assumption you can make. But it's a liberating assumption. And as long as it doesn't lead to contradictions, you're free to make it. The big concern here is that maybe we're missing out on solutions by making this assumption. But linear independence is going to save us from that. We know that if we find two solutions that are linearly independent, those are all the solutions. So we're free to play with assumptions like this and just see what happens. If we do that, that means these first two terms are 0. So the only thing that's left is y1 prime u1 prime plus y2 prime u2 prime equals your input g of x. And these two equations together are what we're going to build our linear system out of. So both of those could be read as differential equations, sure, but they can also just be read as algebra equations, where instead of saying I want to find u1 and u2, I just want to find u1 prime and u2 prime, right? So I think, okay, I've got two equations here. I know what y1 and y2 are, and hence I know what y1 prime and y2 prime are. We can always calculate the derivatives of a known function. I'm trying to find u1 and u2. That's my goal through this whole procedure, is to find the functions u1 and u2 that satisfy this original equation. So here, we've gotten rid of all the u1s and u2s. We just have u1 prime and u2 prime. All the other stuff is dropped out. So rather than having like 4 terms that we're kind of having to deal with and track the relationship between u1, u1 prime, u2, and u2 prime, here we just have 2 equations and 2 unknowns. These are my 2 equations, and the 2 unknowns are u1 prime and u2 prime. That forms a linear system. What's that linear system? It's y1, u1 prime plus y2, u2 prime equals 0. And the second equation is this one, y1 prime, u1 prime plus y2 prime, u2 prime equals g of x. And we want to think of that linear system just as an algebra problem. It's a 2 by 2 linear system. Linear because there's no u1 prime squared or u2 prime squared, right? Linear in the sense of your pre-calculus classes, linear equations. And the nicest way, you could write down solutions to this lots and lots of different ways. You could solve this every time by elimination or by substitution, but fuck that business. We can use Cramer's rule to write down u1 prime and u2 prime. So I remind you what Cramer's rule says. Cramer's rule says if you have a 2 by 2 linear system like this, then you can write down the solutions in terms of determinants of the matrix. In this case, the matrix would be y1, y2, y1 prime, y2 prime, and you should recognize that as the Wronskian matrix. So downstairs here, the determinant of the matrix A is y1, y2, y1 prime, y2 prime. Down here is going to be the Wronskian for y1 and y2. And up here is going to be the Wronskian, but with columns replaced by this, right, your right-hand side. So U1 prime is going to be the Wronskian, but with the first column replaced by 0 g of x, and U2 prime's numerator is going to be the Wronskian, but with the second column replaced by 0 g of x. And one of the reasons we like this so much is because it generalizes nicely to higher dimensions. So if we had a third order system, a third order ODE that we started with, that would yield a 3x3 linear system at this stage. And we would be able to use Cramer's rule to write down the values of U1 prime and U2 prime in terms of the Wronskian downstairs and the slightly modified Wronskians upstairs. So let's do it. Let's write down the result. Solutions. By Cramer's rule. U1 prime equals upstairs here. What did we say? Upstairs, we replace the first column. So you take your Wronskian matrix, your Wronskian determinant, you replace the first column by the right-hand side. So that's 0 g of x. And then the regular matrix A here, which is what's left here is y2 and y2 prime. And you divide this by the Wronskian of y1, y2. And U2 prime, you're going to take the determinant of the matrix A here, which is again y1, y2, y1 prime, y2 prime, and replace the second column by that right-hand side. So you're going to have y1 prime in the first column, and 0 g of x in the second column. And downstairs is that same Wronskian of y1, y2. Okay, this is where W of y1, y2 is the Wronskian. It's the determinant y1, y2, y1 prime, y2 prime. So you could write this formula a bunch of different ways, yeah? You could take this and plug it in downstairs. You could write out what everything is, right? This is 0 times y2 prime minus g of x times y2. And this is y1 times g of x minus y1 prime times 0. But I'll tell you this is how I think of it. This is where I actually start. When solving for yp using the variation of parameters. It's sort of the nicest way I can think of to write the formula. Some people call this W1. Some people call this W2. But I just think of it as Cramer's rule. That's what it is. It's Cramer's rule. Okay. So I think it wise to work at least an example or two. This is pretty scary looking shit, but I want to take a second for anybody who has questions at this stage. Okay. Example time. This is going to take a minute, right? These problems just do take a while, so bear with me. We're going to solve y double prime minus 4y prime plus 4y equals x plus 1 times e to the 2x. This is a problem we could technically solve using annihilators, undetermined coefficients, because this right-hand side is not terribly exotic, right? It is a linear polynomial times an exponential. So we know that the particular solution is going to be a linear polynomial times that same exponential. And you could cook it up with undetermined coefficients. So nice to start with something that you already know how to do. You can trick your work another way. You got to begin with the associated homogeneous equation, which means you need your auxiliary polynomial, which is m squared minus 4m plus 4. And this does factor. This factors as m minus 2 quantity squared. So the complementary solution, because you have a repeated root here, I would write as c1 e to the 2x plus c2 x e to the 2x. In other words, y1 is e to the 2x, and y2 is x e to the 2x. Okay, so the associated homogeneous equation has been solved. We have our complementary solution. We know what y1 and y2 are. y1 prime. So what are we going to need to do now? We need to build up that Wronskian and the kind of Cramer's rule determinants here. So we need y1 prime and y2 prime. y1 prime, the derivative of e to the 2x is 2e to the 2x. Okay. y2 prime is the product rule derivative here, e to the 2x plus 2x e to the 2x. So u1 prime, I can evaluate u1 prime thus by variation of parameters. Yp is u1 y1 plus u2 y2, where u1 prime is this divided by the Wronskian. So that's 0. G of x, which is my right-hand side, x plus 1 e to the 2x. And then y2, y2 prime. y2 is x e to the 2x. And y2 prime, I'm going to factor out the e to the 2x here. That's 1 plus 2x e to 2x. Divided by the Wronskian. So I'll go ahead and calculate the Wronskian as a separate step. Save us some work. Let's crunch this determinant upstairs. This is 0 times this guy minus this guy times this guy. Everybody remembers the formula for a 2 by 2 determinant, right? You take the product of the diagonals and then subtract. So 0 times 1 plus 2x e to the 2x minus x plus 1 e to the 2x x e to the 2x. All of this is over W. So what does that come out to? Well, this first piece here is 0. And over here, I've got e to the 2x times e to the 2x. That's e to the 2x plus 2x is e to the 4x. And I've also got x plus 1 times x, which is x squared plus x. So this is x squared plus x e to the 4x divided by the Wronskian. I'm going to go ahead and do the same thing for u2 prime. Then we'll calculate w. Then we'll integrate to get u1 and u2 from u1 prime and u2 prime. So kind of for me, once I write this step down, I know I'm safe. That's the vibe, right? It's like there's like an element of panic to this. But once you have a safe room, once you've got a place where you know you're good, you can kind of recoup and move forward from there. Upstairs in u2 prime, I'm going to take the matrix, the Wronskian matrix, and swap the second column for 0 g of x. So I'll write it down here. The Wronskian matrix, first column is y1, y1 prime. So y1 is e to the 2x, and y1 prime is 2 e to the 2x. And then the second column, I just replace with 0 and g of x. So 0 and x plus 1, 2x. Downstairs again will be w. And calculating the upstairs determinant, I'll have this times this minus this times this. So that's e to the 2x times x plus 1 e to the 2x minus 2 e to the 2x times 0 all divided by w. This piece is 0. So here I just have x plus 1 e to the 4x. So you've got your formulas for u1 prime and u2 prime. We're going to plug in for the Wronskian w, and then we're going to try to integrate. So this is all where w is the Wronskian of y1 and y2, which is y1, y2, y1 prime, y2 prime, which is that determinant of e to the 2x, x e to the 2x, 2 e to the 2x, x 1 plus 2x, 2x. And if you calculate this guy, you get this times this, which is e to the 4x with a 1 plus 2x up front, minus this times this, which is 2x e to the 4x. So if you have 1 plus 2x times e to the 4x minus 2x e to the 4x, you factor out your e to the 4x. And the 1 plus 2x minus 2x is just 1. So this is just e to the 4x. So you're downstairs here, w is just e to the 4x. It's going to cancel with those, making these integrals really nice. So finally, u1 prime is x squared plus x e to the 4x over e to the 4x. And you cancel and you just get x squared plus x. And u2 prime is x plus 1 e to the 4x over e to the 4x. And you cancel and you just get x plus 1. Everybody with me so far?
Why isn't u1 prime negative?
I'm sorry, could you say that one more time?
Why isn't u1 prime negative?
Oh, did I miss a sign here? Ah, it should be. Yes, yes. Thank you. Thank you, thank you, thank you. That should be negative because 0 minus something. So this is negative, which makes this negative. Yeah, good catch. Thank you. Everybody hear what Maxwell said? I missed this, right? The upstairs here is 0 minus this shit. So this term should be negative. That negative is going to carry down here. This negative. Other questions up to this point? Comments, observations? All right, and now we're ready. We're almost done. I've got U1 prime and U2 prime. Thus, U1 is the integral of negative x squared plus x dx, which is negative x cubed over 3 minus x squared over 2. And you don't need to write any plus c's here, right? At the end of this whole process, there's a lot of like fudging with constants. As you calculate U1 and U2, you can completely ignore the plus c stuff. And U2, integral of x plus 1 dx, which is x squared over 2 plus x. So your particular solution, yp, u1 y1 plus u2 y2 yp is negative x cubed over 3 minus x squared over 2 times e to the 2x plus x squared over 2 plus x times x e to the 2x. Remember, y1 and y2 are those guys. So, therefore, the full solution, general solution, is y equals c1 e to the 2x plus c2 x e to the 2x. And I'll make this is minus x cubed over 3 plus x squared over 2 e to the 2x plus x squared over 2 plus x e to the 2x. There's some more we could do to simplify here. This negative x squared over 2 e to the 2x can cancel with this positive x squared over 2 x squared over 2 e to the 2x. So it's up to you. If you gave me this, I would certainly be happy with it. If you happen to see that the terms here will cancel with the terms here, that's fine also. But this is in that form, right? U1, y1 plus u2. Oh, I left off an x here, didn't I? Sorry. Times x, y2. Oh, and that would mean they won't cancel. Yeah, I take it back. Oh shit, don't cancel. No. You could combine, so then when you distribute this x and hit this guy, you could combine that with this term if you wanted to. But don't bother. I don't think it's worth the time. This takes long enough. I do think you'll agree that comparing this procedure to the stuff that we were doing before, look, here it is. I could have fit that on one page if I wanted to, one side of one page. And that's with all the words and explanations and, you know, not really skipping anything, but not including anything extraneous. When was the last time you were able to get the full general solution to a differential equation on one page? It's been a minute. So that's nice. The variation of parameters thing, very, very powerful. Very, very powerful. And the best part is that it works for other shit too. Like I said, this is an equation we could have solved using annihilators and undetermined coefficients. There are many problems that you couldn't solve using annihilators and undetermined coefficients that you can solve with variation of parameters. So let's see if we can find something slightly more exotic. Okay. It's worth noting that the right-hand side there that I'm using, I call it g of x. That's after putting the equation into the standard form where y double prime has coefficient 1. So when you're going to use this, it's important that you first divide through everything by the first coefficient function. I scam calls every day during this time. Okay, so one more example. This is one we couldn't have done before. Let's solve for y double prime. Sorry, example. Solve for y double prime plus 36y equals the cosecant of 3x. This we could not have done yesterday because cosecant doesn't have a derivative that's a linear combination of itself or itself in cotangent. First, put into standard form. Y prime prime plus 9y equals 1/4 cosecant 3x. And then look at your polynomial, P of m, to get the complementary solutions. It's m squared plus 9. Further. All right. So it's m squared plus 9 times m to the 0. Remember that the y isn't an m, it's the derivatives that are powers of m. So this can be factored as m plus 3i times m minus 3i. It's a difference of squares, it's just complex numbers. Everybody comfortable with this step? We just want to find the roots of this guy. So I can think of this as m squared minus -9, and then the square root of -9 is 3i. So your complementary solution is going to be C1. There's no real part of this complex number, right? I should say M1 is 0 plus 3i, and M2 is 0 minus 3i. So there's like e to the 0x cos 3x, e to the 0x sine 3x, and that's just cos 3x and sine 3x. So C1 cos 3x plus C2 sine 3x. That's your complementary solution. From here, we apply our variation of parameters formula. So we assume that, by variation of parameters, yp is u1 y1 plus u2 y2, where u1 prime is your Wronskian with that Wronskian of y1, y2 with the first column replaced by 0 and the right-hand side. So that's column y1, y1 prime, and then column 0, 1/4 cosecant 3x divided by your Wronskian. And u2 prime is the same. Oh, did I swap the columns wrong? I'm sorry. Yeah. So this is u2 prime. And u1, we swap the first column. In u2, we swap the second column. Sorry. Complicated, easy to make mistakes. So then in u1, we swap the first column with 0 and g of x, and we leave the second column alone. So there, that would be y2 and y2 prime, all divided by w. Some people like to call this w2 and call this w1. And when I show you how to generalize to higher order equations, I'll use that notation too. We need to calculate the derivatives y1 prime and y2 prime. So y1 is here, y2 is here. So also y1 prime is -3 sine 3x. y2 prime is 3 cos 3x, each of those little chain rule derivatives. Go ahead and calculate w here. W is the determinant of y1, y2, y1 prime, y2 prime, which is the determinant of cos 3x sine 3x, -3 sine 3x, 3 cos 3x. And then you take your diagonal products and subtract them. So this is going to be 3 cos squared 3x minus -3 sine 3x times sine 3x, which is -3 sine squared 3x. And that's 3 times cos squared 3x plus sine squared 3x. And this cos squared 3x plus sine squared 3x, that's 1. So this is 3 times 1, or just 3. So that's nice. Your Wronskian here is constant. Because this piece is 1 by Pythagoras. Pythagorean identity for sine and cosine. Alrighty, let's plug into our formulas for u2 and u1, divide by our Wronskian, and see if we can do the integrals. Therefore, let's do u1 prime first. That's this guy. That's plug in here 0. Determinant 0 sine 3x, it's my first row. G of x is the first entry for my second row, which is the right-hand side after putting in standard form, dividing through by the lead term, 1/4 cosecant 3x. And then the second column, second row entry in u1 is y2 prime, which is somewhere here. There's 3 cos 3x. All of this divided by w, which we know is 3. So that's 0 times 3 cos 3x minus 1/4 cosecant 3x sine 3x. That's minus 1/4 cosecant 3x sine 3x all divided by 3. Now, cosecant 3x is the reciprocal of sine 3x. Right? This piece right here is 1 over the sine of 3x. So when you multiply these two, you get 1. By the definition of the cosecant function. So really all you have here is -1/4 divided by 3, which is -1/12. U2 primed, this guy, his first column is y1 prime, which is cos 3x, -3 sine 3x. And his second column is 0 and g of x. So 0 and 1/4 cosecant 3x. All of this gets divided by w. The determinant upstairs, we've got cos 3x times 1/4 cosecant 3x minus 0. So that's, I'll just write it out. Cos 3x times 1/4 cosecant 3x. And this is all divided by the Wronskian, which is 3. And here you're not so lucky. So this is going to be positive 1/12 cos 3x times cosecant 3x, which is 1 over sine 3x. So you could write this as 1/12 tangent of 3x. Because again, cosecant is the reciprocal of sine. Oh, sorry, cotangent. Cotangent. Should. Cotangent of 3x. Sorry, the sign is downstairs. Okay, so to get u1, we have to integrate the constant -1/12. Insert joke about Ramanujan sum here. To get u2, you have to integrate 1/12 times the cotangent of 3x. It might actually be easier to just think of it as cos 3x over sine 3x, because if you don't remember the integral of cotangent off the top of your head, the way you do it is writing it as cosines over sines. So let's do that. So u1 is negative integral 1/12 dx, which is negative x over 12. And u2 is 1/12 integral of cotangent 3x. Now, does anybody remember the integral of the cotangent function?
The natural log of sine.
Good, yeah, it's the natural log of sine. You'd write it as cos 3x over sine 3x and then sub for sine 3x. We got to be a little bit careful here because we do have the 3x inside. It's not just cotangent x. So what are we going to have all together? We know we're going to have a natural log of sine 3x. The integral of cotangent stuff is natural log sine stuff. But what about the constants? There's a 1/12, and what happens to this 3 when we integrate like that?
You divide by 3.
So this will be 1/36. Natural log sine 3x. Now that you've got u1 and u2, you're ready to write down your solution. Write down yp. Yp u1 y1 plus u2 y2 is negative x over 12 times y1, which is cos 3x, plus u2 y2, which is 1/36 natural log sine 3x times sine 3x. And the full solution is y equals c1 cos 3x plus c2 sine 3x minus x over 12 cos 3x plus 1/36 natural log sine 3x times sine That is job done. Again, way faster than undetermined coefficients. In fact, the undetermined coefficients method here wouldn't work, can't be done. Because that cosecant function, it's not one of them that we can guess a trial solution for, because the derivatives don't play nice. No linear combinations of those derivatives play nice. So some alternate notation, how to handle higher order equations, and then we will be done with variation of parameters. Alternate notation and higher order equations. Some people choose to write. I'm serious. So good. Sorry, found out our class, please. Some people write W1 for the Cramer's rule matrix 0 g of x y2 prime, and W2 for the Cramer's rule matrix y1 prime 0 g of x, where and of course W is the regular Wronskian y1 y2 y1 prime y2 prime. And this alludes to how you would set things up in the higher order situation. In the higher order situation, following all the same procedures to cook up your variation of parameters thing, you would end up with an n by n system. So your order n equation, when you apply the same logic, like u1 y1 plus u2 y2 plus un, out to un yn, making the appropriate set of assumptions at the end, you would end up with an n by n system of equations that you're trying to solve for u1 prime, u2 prime, u3 prime out to un prime. And in that setting, you can use this notation. So for a third order equation, we'd have, again, W as the Wronskian of your three linearly independent solutions to the associated homogeneous system y1, y2, y3, y1 prime, y2 prime, y3 prime, y1 prime prime, y2 prime prime, y3 prime prime. All right, that's what the Wronskian for three functions looks like. You just kind of continue the pattern. And you can say that W1, W2, and W3, we'll call them WI. No, that's not a pleasant thing. W1 is what you would get by swapping out the first column for zeros and then g of x. So 0, 0, g of x, and leave everything else the same. Y2 prime, y2 prime prime, y3 prime, y3 prime prime. W2 would be the matrix whose first column is y1 prime, y1 prime prime, 0, 0, g of x, and whose third column is just the y3 prime, y3 prime prime. And W3 is what you think it is. Matrix whose columns are y1 prime, y1 prime prime. Second column y2 prime, y2 prime prime, and his third column is 0, 0, g of x. And then, and with these, we find that ui prime is wi over w. And you could do this here. This would be I equaling 1, 2, and 3, right? So to find u1 prime, you take w1 divided by w. Find u2 prime, you take w2 divided by w, and so on. This generalizes nicely. You can kind of see if you had an order 4 equation, your Wronskian would be a 4 by 4. Excuse me. And then you could define w1, w2, w3, w4 by swapping out column 1, 2, 3, and 4 with zeros, and then your right-hand side, zeros in your right-hand side, zeros in your right-hand side, and your fourth column, same. And then you calculate your u1, 2, and 3 primes by dividing wi's by w's. It really is just Cramer's rule, but it's intimidating. I get that. In this class, I asked you to remember a lot. What I recommend you remember from variation of parameters is the step where I told you this is where I start, right? Or this guy. And then, of course, the obvious u1 ui prime is equal to wi over w, where I is 1 or 2. So this for variation of parameters, this, and of course the assumption that yp is u1 y1 plus u2 y2. That's what I recommend you kind of memorize. All right, that's it. That's variation of parameters. It's really not that bad, and it's awesome in the sense that we can now solve differential equations that were thus far totally inaccessible. Obviously, at the end of this, it comes down to doing an integral. And if that integral is very hard, then the problem will be very hard. Having a formula is wonderful, but it's not a whole lot of use if you can't evaluate the expressions in the formula. I'll tell you, some people will go ahead and give the answers of these differential equations in terms of the integrals. So you find the u1 and u2 prime, and then you just write u1 is the integral of that. You can write it as an indefinite integral or a definite integral from 0 to t. And then just say, okay, this is how I define my function. I'm going to say my solution is given in terms of this integral times y1 plus this integral times y2. Well, that's acceptable in certain circumstances, but I won't put you in that situation. My goal is to see that you understand how to solve differential equations, not to necessarily stress you on the integration, but be aware that the integration can get challenging. You need to remember all the stuff in code too. One last thing before I go. How many of you have heard the name Gil Strang? This is Arthur Maddock. He's a wonderful professor of mathematics at MIT. I took differential equations out of community college just like you guys are doing. This man got me through differential equations. I had a great professor. I love him to death. But he has so many high-level tricks that aren't appropriate for a class at a community college, or indeed a first class of differential equations, anywhere other than MIT. Gil Strang is this guy. He is one of my teaching heroes, a beautiful human being, also a professor of mathematics at MIT. And he has also been publishing some differential equations videos. So if you want to see more on any particular topic, I recommend starting with Arthur Maddock. But most of his videos are from the mid-2000s, 06, 08. Strang's videos are from the last few years, so they're generally higher quality. Strang's handwriting, not great. Maddock's handwriting and board work is beautiful. And both of them will be able to give you more insight, different ways of looking at things, just lots of stuff that I don't have time to go through in class. Maddock, especially when we start talking about the Laplace transform, I highly recommend you watch this video on where the Laplace transform comes from. It will help you a lot. The Laplace transform is a complicated machine. It's a weird animal. You can think of it as the continuous analog of a power series. I'll spoil the thing for you. That's what he says here. But what does that even mean? You got to look at the thing. So that's it from me. Watch MIT. MIT is great. And work hard on the homework. If you need help with anything, come by office hours, send me an email, all of that normal stuff. Study guide is up. All right. Let's see. Is there anything I'm forgetting here? I don't think so. Yeah, your study guide went up yesterday. Your homework is up. It just goes through variation of parameters. That's where the exam will stop. Might as well tell you what's coming, because I guess we've got a little bit of time here at the end. So first, before I ramble on, anything that you guys would like to ask about? We have 9 minutes left.
Well, for me, it was a problem on the homework, but I think it's a little bit lengthy, so it's probably just going to be for office hours.
We could talk through it quickly. What problem was it?
Hold up.
While she's looking that up, I'm going to tell you what's coming. After exam 2, there are going to be a few things that are very challenging, things that I know you guys usually struggle with in the calculus classes. So first, Cauchy-Euler equations. These aren't hard. So beautiful equations. Believe it or not, you've seen them before. I snuck one into your first test, but in a way that you didn't need to solve it. After that, 2 remaining topics are Laplace transforms. And these involve improper integrals. So the Laplace transform of a function f of x, say, is the integral from 0 to infinity e to the negative s x times f of x dx. These scare the shit out of people because you've got to do integrals from 0 to infinity and there's extra variables in there and all that stuff. And then the other thing is solutions by power series, specifically Taylor series. So we'll be using the stuff from Calc 2. This. So if you had any trouble with improper integrals in Calc 2 or power series, and let's be honest, I know everybody did, then you may want to spend some time boning up on that shit before we get into it. I recommend, if you feel well studied for the test, that you watch some of those MIT videos on the Laplace transform, that you maybe review some content from your Calc 2 notes, old tests, whatever, on power series, just to make sure you're comfy with these. These both involve the concept of convergence, which I know is tricky. All right, Millen, did you find that problem?
Yeah, it was number 7. Like, I got my complementary solution, stuff like that. I think I just had a problem with what's it called? Adding stuff over to get my second solution and stuff like
I see. So after we get our complementary solution, if we're going to use undetermined coefficients, we need to take a guess at the shape of the particular solution. So we want, I think one of the things we could run into here is being uncertain as to what the particular solution should look like. So what should our particular solution here look like if we have an exponential and a trig function like this?
Well, I got a ex cosine of 5x plus b ex sine of 5x.
That sounds about right.
What I had for my problem anyway.
So if we have a right-hand side of e to the x cos 6x, then we would want to guess that yp is of the form a e to the x times cos 6x plus b e to the x sine 6x, right? And that's assuming that we don't have anything looking like that in our complementary solution. Remember, if your complementary solution looks like the right-hand side, then you're going to have to introduce x terms here. that was that kind of weird thing, right? Where everything vanishes and you're like, what the hell did I do wrong? Because if your complementary solution is like e to the x cos 6x, which it might be depending on the roots of the polynomial here, the associated polynomial, you may need to slap some x's in front of each of these. Does that make sense?
Yeah.
All right, if we do want to see that in detail, we can do it in office hours, but I think it is about time for us to run. I wish you guys all the luck in the world. Please study hard. This is a tough test. Study guide's up. The sooner you put your solutions to the study guide in, the sooner I can get you feedback. I'll go ahead and enter the grades for your previous study guides. But yeah, try to get your study guide work, or at least some of your study guide work in by Sunday morning. That's when I will go in and give you guys feedback on them. All right, have a good rest of your day, guys. You can come see me in office hours if you want. Otherwise, email, Canvas message. And I'll see you for the test on Monday.